So, we have been discussing about the metal semiconductor contacts, and today we will see in some detail what difficulties one will have to make ohmic contacts on two high band gap semiconductors like gallium arsenide, maybe even wider band gap semiconductors. We will focus on gallium arsenide, indium phosphide, and of course, silicon also will touch upon, because these are common themes for forming the ohmic contact. Okay. Now, what we saw in the ideal case was that the barrier height phi Bn is equal to phi minus chi. So, once you fix the metal, the barrier height is fixed. So, okay, and once phi minus chi is high, you can get rectifying contact on n type substrate. That is what we saw, and you can get ohmic contacts if phi minus chi is high. Same way, if phi minus chi is low, phi Bn is low, and you get ohmic contact onto n type semiconductor and rectifying contact onto p type. Looks very simple, but things get complicated because of this, which we have discussed last time, that is a thin layer of material, maybe dielectric material, and high density of states here in the interface does not give barrier height equal to phi m minus chi, but there is additional drop coming up here. Now, that additional drop I have shown it actually in this polarity. It could be this way or the other way, because if it is this way, the barrier height will be less than phi m minus chi, depending upon what charge is present here, that is depending upon the relative position of the Fermi level to the E naught. You will have plus charge or minus charge. If you have minus charge, okay, it will have some polarity. If you have plus charge, you have some polarity. So, what I am trying to point out is this could either increase the phi Bn from phi m minus chi or decrease. We have gone through the whole thing and ultimately arrived at these three equations. You can see phi Bn is phi m minus chi plus or minus an additional term. Okay, if it is with the polarity that we have shown there, it is minus. If it is other way, it will be plus. So, with taking those things into account, what we saw was the phi Bn gets a new form altogether. Phi Bn is equal to gamma into phi minus chi plus 1 minus gamma into Eg minus phi naught plus this quantity. We saw this last time. Now, gamma is related to the interface state density dit. If dit is 0, that term goes off and you have gamma equal to 1. Okay? You have gamma equal to 1, and gamma equal to 1, this term goes off, and you will have the small term coming up. So, mostly phi Bn will be equal to phi minus chi when gamma equal to 1, that is when dit equal to 0 and also delta equal to 0. So, this both the terms will go off, ideal, okay? That is the ideal situation. But now, when dit is very large, supposing this tends to infinity, then the entire thing becomes equal to 0, which would mean that the first term is 0 and the second term will be gamma is 0 Eg minus phi naught, and this also goes off because gamma is 0. So, you will have only Eg minus phi naught. So, what we are telling is if the dit is very large, if the dit is very large, gamma equal to 0 and phi Bn is Eg minus phi naught. So, it depends upon the difference between Eg and phi naught. So, the phi Bn now depends upon what is the value of phi naught is. Phi naught is actually the energy gap between the neutral level E naught and Eb. Okay. So, that depends upon a particular material actually, the surface condition of the material and actually the material. For gallium arsenide and silicon, it so turns out that phi naught is about 1/3 of Eg. Okay. If it is 1/3 of Eg, then this whole thing will become 2/3 of Eg. We will take a look at that further. So, if gamma is 1 when dit equals 0, as we just pointed out, you will have phi Bn is equal to phi minus chi, which you never get. Experimentally they have found you can't get it, it is always closer to that because of high density of states. Okay. So, due to this, my comment on that is due to high interface state density, phi Bn is equal to Eg minus phi naught, we have seen it just now, okay, because then gamma equal to 0. and for gallium arsenide and silicon phi naught is Eg by 3. So, if this is Eg by 3, the entire phi b n is equal to 2/3 of Eg, and phi b p correspondingly will be, you can see that there. So, this is the total Eg and this is phi naught. Eg phi naught by Eg minus phi naught is this quantity, that is phi b n, that is 2/3 of Eg, and then automatically phi b p will be 1/3 of Eg. Now, we have seen that if phi b n is large, it turns out to be rectifying contact. Okay. Now, here also we just see if this is 2/3 of Eg, okay, or if this is phi b n, the built-in potential here is equal to phi b n minus this quantity E c minus E f, because after all the total quantity minus this quantity, these two, is equal to Q E b I. So, that is that quantity. Now, suppose E f merges with E c, phi b n becomes equal to Q E b I. That incidental I am just pointing out. So, main thing that I want to point out is you end up with phi b n which is large in n type semiconductor, and since it depends only on that E g into 2/3, it is practically independent of metal. Now, what is the consequence now? You have a hopeless situation, you have a very bad situation if you want to make ohmic contact on n type substrate, particularly with materials like silicon, gallium arsenide, etc., or all the wide band gap materials, because the barrier height turns out to be that 2/3 of Eg. Now, you can see that if it is 1.43 electron volts, this will turn out to be about 0.953, which is too large to form a ohmic contact. So, now reiterating what we said, due to high values of DIT, Fermi level pins to E naught. See, what has happened now is the Fermi level has gone and locked on to that E naught level. When you say this is, when you say the high value of DIT makes this quantity equal to phi naught, what he said is that E f has aligned with respect to E naught. We will come back and details of the physics of this little bit we will take at the end of the lecture today. But right now what we say is the Fermi level will align itself with respect to E naught. As a result, this is phi naught. As a result, this is Eg by phi naught, that is 2/3 of Eg. Okay. We will come back to see what is the reason for this locking on to that. In fact, I think we will spend a little time later, because right now my focus is on the ohmic contact. So, once Fermi level aligns with respect to E naught, phi b n is actually equal to 2/3 of Eg. So, it is difficult to make ohmic contacts on gallium arsenide and other high band gap materials, including silicon. Silicon is 1.1 and 2/3 of that is something like 0.75, which is not small. It is not good enough to make an ohmic contact. Okay. So, ohmic contacts are therefore have to be made. This is actually the solution which has been arrived at for making ohmic contacts on n type materials. You have to make using metal semiconductor contact on n plus layer, which is formed on the n layer. Do not put the metal directly on the n type substrate. Form a n plus contact on the surface, then put a metal contact onto that. Then you will, there is a chance for that. We will see how that works out. That is very simple if you look into the energy band diagram. Here what I have shown is the consequence of making the n layer n plus. When you make the n layer n plus, what happens to the Fermi level? Fermi level moves closer to conduction band, but that is locked down to E naught. If it is locked down to the neutral level E naught, that is 2/3 of Eg. So, the consequence of doping it heavily, one is this quantity becomes closer and closer to phi b n. Built-in potential is closer and closer to phi b n. The thing in the diagram that I have shown, Q phi b I is equal to phi b n. Okay. In fact, it will be getting closer and closer to that, and it does not move too much into conduction band. It will be just merging into this E c. So, what you will have will be the phi b b I, which is about phi b n. Okay. That is not what we are looking for. We are looking for more than that. Still, the way it is drawn here, it will be an ohmic contact, it will be a rectifying contact. Now, what other things happen? Let us see. Once we see that this phi Bn is 2/3 of Eg, we know how much is that quantity, that is 0.953 for electron volts for gallium arsenide. That means VBI is actually equal to 0.953 volts built in potential. QVBI is 0.953 electron volts. So, VBI is 0.953 volts. Okay. So, now this, to illustrate it further, I have shown here phi Bn and written the values corresponding to that. For example, here phi Bn is 2/3 of Eg, which is equal to 0.953. Now, from the diagram we have seen that QVBI is equal to phi Bn minus Ec minus Ef, where Ec is the conduction band edge, Ef is the Fermi level, and in the heavily doped semiconductor, Ec minus Ef is very small and extremely, and it can be said it is almost equal to 0. Therefore, phi Bn, therefore QVBI will be equal to phi Bn minus 0, which is equal to phi Bn for n plus gallium arsenide. So, therefore, VBI is equal to 0.953 volt. So, if VBI is 0.953, what are you telling? If you take a PN junction, it is a P, you have got a metal here. So, all that you have done is it is a P, you have got a P plus, you have got a metal here. It is exactly like the PN junction. So, what you have on this side is a depletion layer and an n-type substrate, and this depletion layer, the entire potential VBI is appearing across the depletion layer. Now, let me see where I can just take a look at this. Okay. This actually is metal. Let me change it up. What I was intending to say was, it is almost like a PN junction. Instead of p-type material, you have got metal there, then you have the depletion layer. The voltage across the depletion layer is equal to built-in potential, that is VBI, okay, and that is 0.953. Now, what we are trying to see is what is the depletion layer width there when the doping is very high here. So, now the just like in the case of PN junction, so P you have got the metal there, all the depletion layer is on this side. If it is P plus, there is no depletion layer. If it is metal, there is no depletion layer here. The electric field actually is plus here, minus there, from right to left. Okay. Now, by solving Poisson's equations, you know that the electric field will be linear, peak at the junction, and linearly decaying, it is 0 at the other end of the depletion layer. Okay. What is the peak value of depletion layer? From Gauss law, you can see the peak value of electric field actually is equal to total charge on the right hand side of this peak value, total charge there, that is Q Nd into Wd, that is the total charge, divided by epsilon or epsilon 0. This is from Gauss law, okay, per unit area of course. And they say E peak per unit area, how many field lines are crossing that? The field lines which are crossing that is Q Nd into Wd, so charge is this quantity. Once you know what is the peak electric field is, you can find out what is this voltage is. See, what we are trying to find out is, we know the value of VBI, we know it to be equal to 0.953. What we are trying to find out is, what is the depletion layer width for a particular doping. So, for that we are making use of the expression. So, peak electric field is like this, and once you know the peak electric field, the voltage across that is peak electric field into the width divided by 2. It is actually the area under this curve. Area under this E peak into EDX is the voltage integral. The integral of electric field is the voltage. So, E peak into Wd divided by 2, that is the area under this curve. Okay. That turns out to be, and the plot of that of course is square law. It is like this, integral of that linear function, that is what I plotted here. So, this voltage VBI, that is actually equal to this quantity. This is a well known formula. for a fully depleted region, Q N D into W D squared divided by twice epsilon r epsilon 0, which actually is half of this into W D. Now, that means once you know V B I, we know now, that is why we evoked that. We said phi B n equal to V B I almost. So, that is 0.953 for gallium arsenide. Now, what we want to see is, if I make this doping, so that is fixed V B I, because once phi B n is fixed by E g minus phi naught, that is fixed, and once that is fixed, I can control the width of the depletion layer by changing the doping. Now, I increase the doping, W D will fall. So, just using that expression here, W D is square root of that quantity. Now, you can see V B I is fixed at 0.953, a marginal change will be there with the doping, because logarithmically varying as the doping. So, almost constant. So, if I increase the doping, W D will fall. Let us take the case where the gallium arsenide material, where epsilon r is 12.8, epsilon 0 is free space 8.854, 10 to the power minus 14 farads per centimeter, Q is 1.6 into 10 to the power minus 19, substitute all those things here, and V B I, which we have estimated, seen, because it is equal to E g minus phi naught 0.953, I plug in all these things, and if I put N d equal to 10 to the power 20, very heavily doped, then W d turns out to be 4 nanometers, very narrow. The width of the depletion layer is very narrow now, 4 nanometers, 40 angstroms. That is the diagram now. So, the depletion layer, you see, is decided by that variation. Potential is still 0.953, that phi B n, which you see. So, it apparently it looks as if the barrier height is 0.953, okay. But now what is happening is, the total width here, maximum width is actually 4 nanometers, that width, that is what we have calculated. Depletion layer width is up to this point, that is 40 angstroms, and as you go towards this, the barrier height becomes narrower and narrower, less than 40 angstroms, which means above certain height here, it is as if there is no barrier, because the electrons can tunnel through from either side. So, the barrier height will not be phi B n, the effective barrier height, what I put here is by this line, is very narrow, very small. It is much smaller than 0.953. That is the nice thing about heavily doping. So, when you dope very heavily, whether it is silicon, gallium arsenide or indium phosphide, whatever it is, when you dope it very heavily, the barrier height becomes automatically very small, because whatever barrier is there that is very thin, so carriers tunnel through that. So, for the electrons hardly there is any barrier. So, the carriers can tunnel through these portions, all through these portions, and the effective barrier height is extremely small. Okay. So, that is the key. When the effective barrier height is very small, immediately you can say, now this is ohmic contact. So, if you want to make a ohmic contact, take n type substrate, make the surface n plus, and put the metal on the top of that. So, n plus n is of course the extension of n layer, and the barrier which you are concerned here between these two, if you reduce it, that becomes ohmic contact to that. So, you have a ohmic contact to the n plus region and n plus f smooth transition to the n layer. So, whenever you want to make ohmic contact, what you do is take the n type substrate, put n plus layer by some means, implantation or diffusion, and realize a metal semiconductor contact on the top of the n plus. So, that is the key to making ohmic contacts to n type substrates. So, invariably everywhere you will see a classic example of this ohmic contact in silicon itself is this. What is this? This is actually the transistor in the integrated circuit in silicon. Okay. Now, you can see, just for those of you who are not very familiar, you can see that is n plus layer on the top, p layer, n layer. So, that is the NPN transistor. Okay. The way this is made, just quickly go through that, so that you familiarize with that. Start with a p type substrate. and on the p type substrate you form this n plus layer in this portion, which actually is called a buried layer. Okay. The purpose of that is to make the n plus region to dope the next n layer very heavily there. So, put a buried layer there, n plus layer, that means you are providing a low resistance path for electrons. So, we put that selectively. In fact, you can do that by oxidizing and diffusing only in this portion. Then grow an epitaxial layer, n type layer on the top of that. P type layer, n plus layer in selected portions, then n layer, maybe 10 microns, 15 microns, depending upon the integrated circuit technology that you have got. Today, they talk of that 1 or 2 microns, this layer, whole layer. 20 years back, it must have been 20 microns. Now, it is way down to 1 to 2 microns. Okay, that is the n layer, which actually is a collector region. Okay, now, when you make the, and after that what you do is, you want to have the transistors isolated from each other. So, these regions, P region here, through this window you diffuse P, through this window diffuse P. I am not showing the masking layers etc., just showing the final structure, just going through the process very quickly, just to give an idea what is happening here. So, you had the n layer all through, you can see this is n, but in between you have put a P layer by diffusion. Now, if you connect this layer, so what you have got is this n layer, the cross section of that entire layer that goes like this, the cross section actually goes like that, top view will be like this, what I have shown is the cross section. So, okay. So, you have got the island of the n layer like that. If you see it looking to the top, you have got all through, you have got a P region. So, and another island coming nearby. So, separated by P layer. If you reverse bias the P n junction, each island is isolated by the reverse bias junction. That is called P n junction isolation, which is very popular in bipolar ICs. Not very high performance, but moderate performance ICs. Because in very high performance ICs, you must put a dielectric layer there, because P n junction isolation may not be sufficient. Now, notice here, this P layer is connected to this P substrate, and that is connected to minus P, so that the P n junction is always reverse biased. So, in the IC, the most negative point, okay, the substrate is connected to the most negative point. So, now coming back to this device. So, in this region, this island is the region where you form your transistor. Okay. That is where you form your transistor. So, you can see what is done is diffuse a P layer, diffuse n plus layer for the emitter, and when you diffuse the n plus layer simultaneously, you diffuse this n plus layer for the collector. What is the purpose? Finally, you must put metal to make the contact, ohmic contact. P layer, if you put metal, it will form ohmic contact fairly well in silicon, because 1/3 of Ag, that barrier height is low. So, 5 Vp will be small for this. You do not need to do any treatment there, you get automatically the ohmic contact. Whereas here, automatically, naturally you got the n plus layer, which is the emitter layer. So, you got the ohmic contact, but you form this n plus contact to the n layer simultaneously along with this, so that you have ohmic contact here. If I did not do this diffusion here, what would happen? This metal and this n layer will form rectifying contact. You have a collector with a contact which is rectifying, which is not ohmic. It will block the current flow in one particular direction. So, that is why this ohmic contact is formed by a simultaneous diffusion of this n plus region along with the emitter. Now, you can see, if you want to make a PNP transistor, you will have problem, okay, because you will have to do n plus contact to the n base region. That has got to be a separate step. Here, this step is automatic with that step, but in the PNP transistor, it will be P plus, this is P region, that P plus can be done. But what about this n region that is base? If a P there will be n, you must put an n plus region, that has got to be a separate step. This is one of the difficulties when you want to make PNP transistors. In fact, if you carefully see, the PNP transistors are costlier than NPN because of that additional step of forming the n plus contact. You may say, after all, one more step. It is not just one more step. You have to oxidize, open the window by lithography, okay, etch the oxide, then do the diffusion. So many steps are there. When you do so many steps, the chance of defects coming in, contamination coming is more, and the result will be yield will go down. That is why the cost is more. Okay, this is just to illustrate the power of why n plus layer is put in the structure. The whole reason is that is the high DIT making the barrier height large in the n type substrate, making that rectifying if you do not have the n plus contact. Okay. Now coming to gallium arsenide, how do you form that? People have tried various tricks. Okay. One of the tricks which is working out universally is n type gallium arsenide. See, after all, what you need to do is realize a n plus layer on the top, onto which you can put a contact metal. So what is done is evaporate gold-germanium onto gallium arsenide, okay, and gold 88% by weight, germanium 12% by weight. In fact, when a germanium 12% by weight would correspond to about 27 atomic percentage of germanium. Okay. So you evaporate that and then heat up this in a nitrogen ambient, or better with the hydrogen and nitrogen to prevent any oxidation. So allow it at 400 degree centigrade, just 1 minute. All that happens in 1 minute. So what happens here is the gold germanium. Okay, if you take a look at the phase diagram of gold germanium, gold. I am recalling you back into the gold germanium, the phase diagram, that is germanium. Okay. So if you take germanium, 100% gold, that has a melting point of 1060 degree centigrade, melting point, and germanium has a melting point of about 940 degree centigrade, around that 936 or so. Okay. That is the melting point. Now when you mix them together, the phase diagram is something like this. That you have a line here. Let me just see if I have those numbers here. I thought I have noted down some of those numbers. 363 degree centigrade. Okay. If you remember, just draw it once rather like this, almost comes like this. Okay, or rather like this, whatever way it comes. Okay. Now that is a liquid. Liquid plus solid, solid. Liquid, liquid plus solid, and solid. That is when you come down from this side like this, there will be precipitation of solid, and the composition of solid will be given by this curve. Okay, liquid plus solid, and this is solid. Okay, you do not have to worry about that. What I am focusing is this point. From there, this is liquid. In the sense, whatever composition is there, vary gold from 100%, melting point is 1060. And if germanium alone is there 100%, melting point is 940 degree centigrade. If the composition is 12% by weight, germanium, at that point, that is the melting point. What we are telling is, there is a melting point for gold germanium which is lower than either gold or germanium. when the composition is 12% by weight or 27% atomic number, atomic percentage. Okay. That is 27 atomic percentage of germanium or 12% by weight, the melting point is 360 around 360 degrees centigrade. So, nice thing that happens is you go to 400 degrees centigrade, somewhere up there, slightly above. Okay, there are two things happen. The mechanism by which you get, ultimately what happens is when you do this alloying at 400 1 minute, you get the ohmic contact nicely onto gallium arsenide. The mechanism is like this. The gallium from the substrate, gallium arsenide, okay, moves towards the surface. Okay. In fact, when you go to temperature slightly more than the eutectic, this is the melting point. If I go slightly more than that, you are going onto this point. Okay. I am telling this point because this becomes less gallium there, less germanium. Okay. Germanium concentration comes down here. What happens is the gallium from the substrate moves up to the molten layer. This is the molten layer on the top. Okay. It moves onto this top layer, and from the top layer germanium moves down. So, gallium moves up because gallium has got a lot of great affinity towards gold, let us put it that way. So, it moves towards the surface where this is actually in a molten stage. Okay. So, you go slightly up above that temperature 400 degrees centigrade. If still liquid, the germanium concentration can come down from there, still it will be liquid state, and that germanium concentration, it has come down. Why it has come down? It has gone down to the gallium arsenide. So, all that happened is gallium has moved up to the gold germanium, and germanium little quantity has moved down to gallium arsenide. And where is it sitting? Germanium is sitting where the gallium has moved out. That is what we said here. Germanium from gold germanium diffuses and occupies gallium vacancy, V gallium, making the layer N plus, forming the basis of ohmic contact. Germanium is fourth group element. So, gallium has moved out to the surface, that means gallium vacancies are created. So, germanium goes and occupies the gallium vacancy. So, it makes it N type, N plus, because lot of germanium is there, 10% is large number compared to total number of gold germanium is present there of the order of 10 to the 20. So, you will have these ohmic contact formed. Okay. So, the key thing, this is the most successful ohmic contact that has been made on gallium arsenide. What about p type? In fact, even in p type, if you want to make a good contact, you better make it p plus. The moment you make it p plus, the barrier thickness becomes very small. As a result, the effective barrier height becomes very small. Okay. So, what you do is, instead of gold germanium, you put gold zinc. Zinc, some percentage is there, not exactly 12, slightly different. You get actually alloys of gold and zinc, you can buy it. You can buy gold germanium alloys. If you do not have, how do you make gold germanium contact? You do not sit idle. You weigh gold, you weigh germanium, 12% of that, put them together in a boat, melt them together, you operate, you get gold germanium. Similarly, you can do zinc. So, gold zinc alloy at about 400, okay. Zinc occupies gallium vacancy. The key thing is, when you have the molten gold compound, gold germanium or gold zinc, gallium moves up to the layer, creating gallium vacancy. Whether it is becoming N plus or P plus would depend upon what is moving down. If it is gold germanium, germanium moves down, making it N plus. If it is gold zinc, zinc is P type. So, that makes it P plus. So, you make P, once you make it P plus, it is a very good ohmic contact. What about indium phosphide? Indium phosphide same trick. After all, gold-germanium, instead of gallium moving up, indium will move up and germanium will go and occupy that position to make it N plus. Here zinc will move down to occupy the indium side. So, you get good Ohmic contact on N type and P type. Now, few things more I want to discuss. In fact, I have deliberately kept it open here today, because some of the things which I have promised that I will discuss. I do not have this in the slide, but I will go to the board and explain those things to you. Okay? We have some time left on to which we can discuss very clearly. Number 1, what we said is the DIT distribution. I promised in the last lecture that we will discuss this sometime. So, I got some time here to discuss this. We said on the surface, this is EC and this is EB. What we said is this interface density will be distributed all over this all over the band gap, okay. And this is due to the dangling bond. So, it is like introducing an impurity. In the bulk of semiconductor, if I introduce a dopant, what do you get? You get a level. Any deviation from periodicity gives a level. So, in the bulk, what you got here, okay, that here, in fact, you draw it like this. These are the donor levels. You draw it, you do not draw a continuous line there. You draw either like this or dotted lines, okay, and all these levels, each one of those correspond to one donor, and the entire thing corresponds to one level. Now, this actually is against Pauli's exclusion principle. What does Pauli's exclusion principle say? No two electrons can occupy the same level, but here you see when it is occupying, it occupies the same level. It is valid under certain conditions. It is valid so long as these atoms are far away. Okay. If the atoms will be far away, if the number of atoms are less, that is, if the doping level is low. Low meaning 10 to the power 16, 10 to the power 17, 10 to the power 18, still it is low, because silicon number of atoms per centimeter cube is 10 to the power 22. So, compared to that 10 to the power 16, 10 to the power 17 is low. But if you increase the concentration, what happens? The atoms come closer and closer. Once they come closer and closer, what happens? The wave functions interact with each other, and instead of one level, you get multiple levels. So, when you dope heavily a semiconductor, that single level which is donor level splits up into number of levels. Okay. You can no longer talk of, when heavily doped semiconductor, you can no longer talk of a single level, you will talk of a band of energy. It can even merge with the conduction band. That is the situation that you have when you have that. So, multiple levels are there. It is just like the energy band formation. How is the energy band formed? How do you get the conduction band? The conduction band is formed because there are silicon atoms which are nearby. The electrons in the outermost shell interact with each other, and multiple levels you get. Same thing happens with impurity when the impurity concentration is high. Now, let us take a look at. So, that is the same type of impurity can give energy band, split over. As you keep on increasing doping, the impurity band becomes wider and wider. Okay. Now, take a look at this surface. This is the surface. And we said there is surface states are there. And what are these surface states due to? Due to loss of periodicity. Okay. So, due to the dangling bond. Now, this dangling bond or this particular surface atom can either donate that electron be a donor or accept an electron further, because it needs some electrons. It can accept an electron to complete the bond and be an acceptor. Now, the question is, so that means actually it can act as a donor or an acceptor. Some of them will be formed donors, some of them will form acceptors, okay? Because depending upon the situation, some of them will accept electrons, some of them will donate electrons. Now, we also said, so that means actually let us see this. So, that means instead of, you can't represent it by one level, you cannot represent that either donor level or acceptor level by one level. Okay? Even if you say it is one donor level, since there are 10 to the power 15 atoms per centimeter square on surface, that many levels are there, and they all cannot stay on the same level because uncertainty principle. You cannot have the same level. So, that splits up because number of atoms is so large on surface. See, when you say 10 to the power 20 per centimeter cube, it is in volume. Same number is there on surface when you talk, it is 10 to the power 15. So, you have got actually now very large number of defect states on the surface. So, that means actually very large number of levels are there, all of them split up, and that is why you get the entire thing splitting up on this band gap. Instead of one level, you have got these states spread out, just like this splits up into a band, this has split up into a band on the surface. So, you have got those surface states, large density of states distributed all over the surface. Now, as I said, it can be donors or acceptors. Where will the donor level be? We said there is a neutral level. We said there is a neutral level E naught somewhere, which is characterized that particular material. And we said below that there are donors, above that there are acceptors. How are you justified this? This we said is acceptor, this is a donor. Okay. We said, let us put it here, E naught is that level, all these are donors and all these are acceptors. How do we say that? Usually when you talk of semiconductors, shallow donors, we say it is near conduction band, shallow acceptors, we say it is near valence band. What is the meaning of that? The meaning of that is, when you put the donor level near conduction band, the meaning is the energy required to remove that electron and donate to the conduction band is very small. That is possible when you are introducing that fifth group in silicon or fourth group in the gallium site. So, one extra electron is present which is free to move, and that can be very easily removed. Okay? That is the idea. So, that is why you locate the donor level there. Similarly, the acceptor level you locate it here shallow, that is called shallow level, because it can easily accept electrons in the valence band to that. That means, when the electron is accepted from valence band to that level, it has donated a hole to the valence band, but it gets ionized. When you say donor is ionized, what you say is it has donated electron to conduction band. When you say an acceptor is ionized, it has accepted an electron, but donated a hole to the valence band. Both are donors, if you look into it. One donates electron, one donates holes. One donates negative charge, other one donates positive charge. That is the key. So, when the donor level donates electrons, it becomes positively charged. When the acceptor level donates a hole, it becomes negatively charged, because it takes an electron. Now, but here we are talking of the reverse situation where donors are here. I will illustrate that with an example of gold in silicon. Gold in silicon gives multiple levels, okay? Because that is very simple to understand. Once you understand that, you can easily understand this. Okay? Now, let us take a look at gold in silicon. Gold has got one electron, valence electron, and it can go and occupy the lattice site in silicon very comfortably. So, if it can occupy, what happens? Gold, silicon, I am just taking this example because very easy to understand. This is a thing which is encountered often. Silicon. Now, if you see, that is the electron available for gold, okay, and then that is the silicon. Silicon, electrons from silicon or 4 are there. If this were silicon atom, what would happen? 1, 2, 3 bonds would have been formed totally. All the bonds are formed if this were silicon. Unfortunately, this is occupied by gold, which has only 1 electron. Silicon has got 4 electrons, which satisfy all the bonds. So, only 1 bond is there. Now, this gold can behave the way it likes, in the sense depending upon situation. It is again an amphoteric material, gold in silicon. It can behave as an acceptor or a donor. Now, let us see, this can donate this electron. It can donate this electron. Now, to donate this electron, you must remove the electron, take it to conduction band. How much energy will be required? Okay, if this is a silicon atom, if I break the silicon atom, how much energy, break the bond and donate it to conduction band, how much energy was required? 1.1 electron volts. Now, this gold atom size is different and etc. So, this energy required is not exactly 1.1. If it is a donor, it would require less than 1.1 electron volts, not 50 millivolts and all that. You cannot break this with very small energy, because it is not the 5th electron of the donor of the phosphorus also. So, what happens now is EC and EV. The donor level, due to donation of this electron, will be located far away from the conduction band, somewhere here. It is not actually exactly equal to 1.1, it is this is 1.1 electron volts, this is something like 0.3 electron volts. That means, this is about 0.8 electron volts. So, almost large energy is required to break this, but it can still donate. Okay? Now, let us take a look at this, because this explains now that your donor level is closer to the valence band. This is a deep donor. Why it is a deep donor? Not because it is lying deep in semiconductor. It is a deep donor because it is deep in the energy band diagram, far away from the conduction band. If it is very close to conduction band, it is called a shallow donor. If it is very far away from the conduction band, it is called deep donor. It is a deep donor. It requires a lot of energy to take the electron from there to there, to the conduction band. Now, there is a chance that instead of donating, it may find it easier to accept an electron. Supposing it accepts an electron, what happens? This is the donor and this is, instead of donating, it accepts an electron. That is another way. And when it accepts an electron, where will I put the energy level diagram now here? Corresponding to that, there is a level. When you say there is an acceptor level, you must be able to locate it in the energy band diagram. Now, I have identified this particular location closer to valence band because it requires a lot of energy to remove those electrons, because it is like the bond in the silicon. Now, once you have identified this level very close to valence band here, 0.3 electron volts above the valence band, where will you identify the acceptor level? Will you identify it above or below? That is the only question that I am asking. It will actually, you have to look at it from the point of view of energy. When it is donating the electron, if it has donated, it has got charged positively. Okay? It requires certain amount of energy to take the electron from infinity to that point. It is easier to take because plus charge. Suppose it is accepting an electron, okay? Will it require more energy to take electron to that point compared to this, or less energy? Because when it is accepted, the charge state of this is negative. If it is donated, the charge state of that is positive. Please understand, when a donor donates, it becomes positively charged. An acceptor accepts, it becomes negatively charged. So, that is negative charge. If it is accepted, instead of donating, if it has accepted an electron, it has become negatively charged. Two situations. So, this level corresponding to this acceptor level will be above this. I will put that. GaEd. So, I will go through that now once again, because if it has donated, I have identified that the energy level is closer to valence band, because it requires more energy to break that bond. So, having said that, instead of, so the energy level is 0.3 electron volts, 0.3, around that electron volts above the valence band. Having said that, suppose instead of donating, if it were accepting, it would have negatively charged. So, between the two states, the donor state and acceptor state, if I am trying to bring an electron, let us say there are two atoms, one atom donated, one atom accepted. It is not the same atom that is doing the job. One atom donated, one atom accepted. There are 10 to the power 15 gold atoms. So, if you have taken the electron from infinity to that point, to the donated gold, you have to spend certain amount of energy, that is marked by the Ed there. Now, there is other atom which he has accepted. So, between the two of them, that is, one is donated, other one is negative, accepted. It becomes easier to take electron to this point compared to taking electron to this point. To take an electron to the negatively charged site, you have to spend more energy. So, negatively charged site will have more energy compared to that. So, what I am trying to point out is, you have got a situation now where the deep donors are below, or the same type of impurity, if it is donating and accepting, the donor levels will be below and the acceptor levels will be up. Now, that has come up here. The donor levels are below, the acceptor levels are up. Now, you have got some of them donating, some of them accepting, but all those which are donating, if it is only one which is donating, it will have one level. There are hundreds of thousands of them they are donating, they spread up into donor band, that is the donor band, and all the acceptor levels are above that, exactly same situation. Okay. So, you get a donor band and an acceptor band, and separated by a neutral level. Neutral level in the sense, if the Fermi level is here, if the Fermi level is coming to this point, the levels above that will be not occupied really, okay, and levels below that will be occupied. That whole thing will be neutral. Let us go back to the diagram and see now what happens if I take a semiconductor which is having a free surface, which is a surface which there is no metal. Okay, let me just draw that. I still have few minutes left, so I can just discuss that quickly. If I have not finished it, I will come back to this next lecture. Okay, I have the conduction band, valence band, n-type semiconductor, n-type semiconductor. This is a surface, that is a neutral level. All these levels are occupied and all these levels are not occupied now. If it is not occupied, neutral. If the Fermi level is, this is a free surface, no metal, absolutely no metal, I have taken a semiconductor surface like that. If I take a look at that, what will happen will be, because of the high density of states, no oxide, nothing, just a bare semiconductor. Okay, we are talking of a bare semiconductor surface. Okay, what will happen now? This is n-type. There are, what is the charge here now? What is the charge on the surface? Fermi level is above the neutral level. All the levels below the Fermi level are occupied. What is the charge state of this? Donors are occupied neutral. These are acceptors occupied by electrons, negative. So, this is negative charge. All these states are negatively charged. Where does the negative charge come from? It has accepted electrons from the semiconductor. If it has accepted electrons from the semiconductor, what will happen? N-type semiconductor electrons have been removed from some region. It will have removed some region here. So, this region has contributed to the electrons here. Okay. That means, this region will be depleted. I think I will discuss this next lecture, because this is a very important concept. Even if you take what emerges from here is, even if you take a free semiconductor surface, do not put any metal, that will have a depleted surface, because these electrons will have to supply from this one. So, entire energy band diagram will bend. Okay. That aspect is a very interesting aspect, which hurts the MESFET. When you make the MESFET in enhancement mode, that is the difficulty people have. So, you will have depleted surface. This concept of some of these things I will bring in the next lecture, before I go on to the IV characteristics of them. So, we will see you next time.